alkyne. Okay, chapter 9, new family of the organic molecules, alkyne. The general formula for alkyne is going to be CnH2n minus 2. For alkane, we had for alkane, the general formula was CnH2n plus 2, alkene CnH2n, and alkyne okay. So if you compare alkane to alkyne, you see you're missing like 4 hydrogens, right? Because this is a 2n plus 2, this is a 2n minus 2. If you are missing 4 hydrogen, and every 2 hydrogen accounts for 1 element of unsaturation, like a 1 pi bond, then alkyne, with just 1 functional group of alkyne, is going to have 2 elements of unsaturation. So a CC triple bond is 1 sigma bond and 2 pi bonds that we have CC in the CC triple bond. So 1 sigma bond, 2 pi bonds, 2 elements of unsaturation. General formula CnH2n minus 2. So triple bond, CnH2n, 2 elements of unsaturation. Some of these reactions, they are like alkene, and there are, because you have the pi bond for alkyne, and if you break a pi bond, you could add 2 sigma bonds. For every pi bond you break, you could add 2 sigma bonds. For this family, just like alkene, you want to know about general structure and the physical property of these compounds. You want to how to name these compounds, how to prepare these compounds, and what are some of these reactions. So if you have like a summary sheet for your study for the final, for each of the chapter or each family, if you start just talking and writing and summarizing in a way that you can do like a storytelling, you can talk to someone else and say, okay, about alkyne. So there are 4, like when you're writing an essay, your first paragraph or like introduction, and then you have a paragraph or supporting. So what you have here is like 4 aspects for each family. That's for alkane, alkyl halides, for alkene, and then alkyne. How to name these compounds, what are physical properties, how to prepare these compounds, and what are chemical reactions. And then like you can add detail about how to prepare this compound in a summary sheet, like a page or 2. It's very helpful and it's very useful. I saw that they're like selling like $30 a piece, a summary sheet for organic 1, this chapter or that chapter. You can make your own summary sheet, and it helps you to learn, and it remember, and it helps you to prepare for your exam. And it saves you a lot of time, because the night before the exam, you cannot read the entire book or go over the 10 chapters. But if you have summarized it before, it's going to make it much easier for you. So for nomenclature, very similar to naming of alkane, you find the longest carbon chain. You want to make sure that longest carbon chain is going to include the triple bond. And location of the triple bond needs to be indicated if it's by a number, and you change the A and E to Y and E. So alkane changes to alkyne. If there is any branch, you are going to name and a number and name the branch. Branches are given with the alphabetic order first, and then the major or the main carbon chain. Okay. Examples. In this case, in the first example that we have here, you have two functional groups. You have alcohol functional group and alkyne functional group, alkyne functional group and alkene functional group. Alkene actually takes the takes priority here, and you would number from this side 1, 2, 3, 4, and 5. So this new and old, this new IUPAC naming is like from 1997, is not very, very new and is not very old. So it's fairly recent.
Excuse me, Professor. I think we're still stuck on the other PowerPoint for Chapter 8.
Yeah, I was going to say that too. I didn't know if I was going crazy or not.
I thank you so much. I'm glad that you said something. Hopefully.
There we go.
Okay. So for this molecule, the first molecule, you have carbon 1, 2, 3, and 4, 5. Two functional groups, functional group alkyne and alkene. When you have multiple functional group in a molecule, you must first determine which one takes the priority. Between alkene and alkyne, alkene actually takes the priority. So you number it from left to right. So any carbon that does not take a number, it would be named as a branch. There's only one branch here, methyl group on carbon number 2. So it's a 2 methyl, 1 pentene, 3 ine. So 3 ine, this is just a combination of the functional groups. If you only had one functional group, we just put an example with just functional group, one functional group. So you have 1 carbon, 2, 3, and 4, and you have a methyl group here. For this name, when you are naming this compound, you are going to start numbering from left side, right side, because it's closer to the carbon-carbon triple bond. Carbon-carbon triple bond takes priority over the branching. 1, 2, 3, 4, and 5. So you have a carbon that did not take a number, so that is a branch on carbon number 4. So it's going to be 4 methyl. So you have the number separated from the letter using a dash line, 4 methyl, and then the alkyne functional group starts on carbon number 2. So all you have to say is the 2 pent, 5 carbon, pentyne. So pentane, and then you change the A and E to Y and E, 2 pentyne. So 4 methyl, 2 pentyne, you don't have to say 2, 3, just like alkene, that you didn't have to say the higher carbon number. That means that it starts with carbon number 2, and definitely it would go to carbon number 3. When you do have multiple functional groups with the new IUPAC naming, you can just give the location for each functional group, and then bring the functional group like a 1 in. That means that you have on carbon 1, you're starting carbon-carbon double bond, that's in, and then you have 1, 2, 3, 3 ine or 3 wine. For alkyne. For the OH group and then the alkyne group, you have 2 functional group. You give the total number of carbon in the longest carbon chain. Then you have to give the old one. For me, it's easier, but both names are acceptable. I mean, the old and new IUPAC is acceptable. For me, the old naming of the IUPAC, when you have multiple functional group, it rhymes better. Like you have 3 butine, 2 ol, rather than but, 3 ine, and 2 ol. So the old one looks, for me, is easier. but both of them are acceptable. Okay. Ether functional group, alkyne functional group. Alkyne takes the priority. So you have your numbering from the side that is closer to the triple bond. 1, 2, 3, 4. On carbon number, I'm sorry, 3, 4, and 5. On carbon number 4, you have a methoxy group. Methoxy group is like methanol, and you drop the H. So if you have like a CH3OH, you remove the H, you have CH3O. Methanol changes to methoxy. So methoxy is like the OR group from the alcohol. Alcohol without the hydrogen is, in general, is called alkoxy. If it's 1 carbon would be methoxy, 2 carbon would be ethoxy. So if you have like a CH3, CH2O attached to a main carbon chain, this is called ethoxy. So ethoxy or methoxy group in this case is attached to carbon number 4. And then you have 2 hexyne. Keep missing the common name for these compounds. They are basically, they base the name on the acetylene. Acetylene is the smallest unit, and that is like a CC triple bond. The formula for acetylene. Okay. So now if you remove this hydrogen and change it to methyl group, then based on the common name, it would be methyl acetylene. And if you change this hydrogen to another methyl group, it's going to be dimethyl acetylene. And if you have this bulky group here, if you have an isopropyl, and on this side you have an isobutyl, then it would be isobutyl isopropyl acetylene. So basically, what are the groups that are attached to the acetylene? These are common name. Okay, naming is not, too much covered because it's a short chapter anyway. The rules that applies for naming alkene and alkane, it all applies to alkyne as well. Physical property, these compounds are non-polar, and the intermolecular forces that you find in these molecules, it's dispersion forces. These molecules are water insoluble, and because it's London dispersion or dispersion forces only, the boiling points are going to be low. Melting point is going to be low for compounds that they have a low number of carbon. But the longer the carbon chain is, the melting point and boiling point is going to increase, because boiling point and melting point depends on intermolecular forces, and for dispersion forces, it depends on molar mass. The greater the molar mass, the stronger the dispersion forces is going to be. Uses of acetylene. Acetylene is used in welding. It generates lots of heat and flame. Okay. Have to prepare acetylene. This is basically you're starting with carbon and then calcium oxide. If you mix the carbon or charcoal with lime, which is calcium oxide, you get calcium carbide. You have calcium carbide, add water to calcium carbide, you end up with acetylene. Then from the acetylene, you start with acetylene, you can replace the hydrogen with the alkyl group. So if you have acetylene and you add a base, you can remove the hydrogen. So let's say you have acetylene, you add sodium amide, NH2 minus. This is a very strong base. It's going to remove the hydrogen. So if you remove the hydrogen, you end up with acetanilide ion, negative charge. And this negative charge, it's going to make this piece a good nucleophile. And if it's nucleophile, it can attack alkyl halide. So if you have acetanilide plus ethylene bromide, let's say, CH3, CH2Br, you have a leaving group, you have nucleophile, so it can attack this carbon and leaving group would leave. The net result is going to be alkyne with 2 carbon you already have from acetylene. You're getting 2 carbon from ethyl group, add a new 2 carbon, and it's going to be CH2, CH3. Just please make sure that this is like a common mistake. Sometimes the students, they write like this, and instead of writing CH2, CH3, they write CH3, CH2. 2 problems. You are giving too many bonds to CH3, you're giving 5 bonds, that's impossible. And then you leave the CH2 last, which doesn't have enough, or it doesn't have 4 bonds and is not going to be happy with less than 4 bonds.
I'm sorry, I don't want to get off the topic, but what does it mean when it says heat coke with lime? What is the coke part?
Coke is the other name is for carbon.
Okay.
Charcoal, yes. In industry, they call it coke. So it's like a pure carbon. You mix it and heat it up with lime, which is the calcium oxide, and that would give you the calcium carbide. The calcium carbide in water would give you acetylene.
Thank you.
You're welcome. Hybridization for alkyne, of course, is a sp hybridization. The bond angle is 180, and the 2 pi bonds that is forming from the overlap, side by side overlap of 2 anhybrid p orbital. If you look at chapter 2, we have the sp hybridization covered there. What is, okay. Bond length for triple bond is shorter and the strength of bond is stronger. The short, look at this pattern, you might get questions like this. Single bond going to double bond to triple bond, the bond gets shorter, but it gets stronger. So if you want to break the triple bond, you have to spend a lot more energy compared to double bond or compared to a single bond. Alkynes, sp hybridization is going to give the alkyne, terminal alkyne, rather more acidity. So terminal alkyne, the hydrogen is more acidic than alkene and alkane hydrogens. So the more S character of the hybridization for the carbon carrying the hydrogen, the more S character, more acidic is going to be. And because it's acidic, you can bring a strong base, remove that, and you change that acetanilide ion, as I said, because it's acidic hydrogen, you can remove it. But you have to have hydrogen attached to carbon-carbon triple bond in order to remove it with the base. If it's internal, there is no hydrogen attached, so it's not acidic. So after you remove the hydrogen, then you can add that to alkyl halide. But this slide doesn't show addition to the alkyl halide. It just shows that you must have a terminal, you must have the hydrogen attached to terminal alkyne in order to react with the base. Like this example with 2-butene, there is no hydrogen attached to carbon-carbon triple bond. As a result, it's not going to react with the base. When you have the acetanolide, it can react with the alkyl halide as a like a SN2 type reaction. Acetanolide acts as a nucleophile and the leaving group would leave. The result of the reaction is alkyne with longer carbon chain. How many carbon are you adding? It depends on what alkyl halide you add or you make it react with. If your alkyl halide is a methyl iodide, then you only add 1 carbon. If it's an ethyl iodide or ethyl bromide, then you're adding 2 carbon. If it's like an isopropyl, then you're adding 3 carbon. So it depends on how many carbon you are bringing from the alkyl halide. You can add that number to the acetanolide ion. So you can increase the number of the carbon chain, or length of the carbon, or the number of carbon in the carbon chain can be increased. Okay, since I don't want to change the